In this video, we'll go on to talk about two important aspects of working with the derivatives of implicitly defined functions, and that is to find out the points at which the graph has horizontal or vertical tangents. And because these particular equations produce very unusual types of graphs, these could happen in many places. And so we're going to allow the calculus of this to tell us where we have horizontal tangents and vertical tangents. And very simply, when we have, which we will often have in these cases, a derivative that turns out to be a rational function, well, we'll have horizontal tangents whenever the numerator is 0, and vertical tangents whenever the denominator is equal to 0. So let's get started with number 57. We'll take the derivative of both sides with respect to x. When we do that, derivative of 25x squared becomes 50x. Derivative of 16y squared becomes 32y, y prime. The derivative of 200x is just 200. Derivative of negative 160y is negative 160y prime. And the derivative of 400 is 0. Derivative of 0 is also 0. So the calculus part is done. Next, we want to collect the y prime terms on the left side. So we'll have 32y, y prime minus 160y prime. Then we'll move over to the right side at negative 50x minus 200x. Factor out the y prime, divide by 32y minus 160. We end up with y prime is equal to, that 200 should just be 200 and not 200x. So on the right side we have negative 50x minus 200, and then I factor out a negative 1 and I get negative quantity 50x plus 200 divided by 32y minus 160. So going back to our original statement that horizontal tangents will occur whenever the numerator is 0. In this case they will occur whenever 50x is equal to negative 200. Or x is equal to negative 4. Now, it's not enough just to know that x is equal to negative 4, because this is not just a function here. This implicitly defined, this implicit equation is very unusual, and it could have many y values that have an x coordinate of negative 4. The only way we're going to find them is to go back to the original function and plug in x is equal to negative 4 and solve for y. So we'll have 25 times negative 4 squared, quantity squared, plus 16y squared, plus 200 times negative 4, minus 160y, plus 400 equals 0. Now we simplify. Negative 4 squared is 16, 25 times 16 is 400, plus 16y squared minus 800, minus 160y, plus 400 equals 0. And fortunately, the 400, negative 800, positive 400 will zero out. We'll be left with 16y squared minus 160 equals y. If we factor out from that a 16y, we'll see that when x is negative 4, y will be 0 or 10. And so those are the points where the curve has a horizontal tangent at negative 4, 0 and negative 4, 10. Now we want to do the same thing with vertical tangents. We've said that the vertical tangents will occur when the denominator is equal to 0, or 32y equals 160, or y is equal to 5. Similarly, we're going to go back to the original function and plug in y is equal to 5 and solve for x. So we have 25x squared plus 16 times 5 squared plus 200x minus 16 times 5 plus 400 equals 0. 16 times 25 is 400. 160 times 5 is 800, and again 400 minus 800 plus 400 zeros out, and we're left with 25x squared plus 200x is 0. Factor out of 25x, we get 25x times x plus 8 is 0. So when y is 5, x will be equals 0 and negative 8. So 0, 5 and 0, negative 8 will be the points on the graph at which there are vertical tangents there. So this is it's a cool process for finding vertical and horizontal tangents when the numerator and denominators are 0.